So hello everybody, and tonight we will talk about finite elements. Basically what I want to talk about here is about a little finite element solver that I've written once, which implements hexahedral elements with bubble functions. So basically it re-implements the basic element that ANSYS uses if you don't specify a specific element for static calculations. So there's a little static calculator written from scratch in C code that I want to show you, and I want to use this basically this little tool to get you a little overview of finite elements and what this is all about. I know this is not for simply bioinformatics, but also very interesting and more physics-based and more mechanics-based. But I think this is also something that your viewers will be interested in. Just tell me what you think about it. If you find this useful, please cite this here with this Zenodo record, so you get the DUI. If you click on this, we will put it down in the comment section somewhere. So what is this all about? What are, first of all, in order to understand finite elements, what are hexahedrons? What is the basic element of this finite element solver? So hexahedrons are objects like this, so they have 8 corners. They are cube-like, let's say it like this, but they're not at all like a cube if you think about it, because these corners can be at any position. And they are connected by straight lines from one corner to the other. But of course, if you do this, if you think about it, if you look just at the top surface here, a 7 is not in the same plane as these 3 others might be. You get uneven surfaces or sail-like surfaces if you want to. Yeah. So the corners can be anywhere in space, basically, as long as the volume here is bound up is positive. Yeah. They can, and basically if they are connected to each other, as I said, with straight lines and span up these things. The orientation is important, so you have to number your corners right, because otherwise you get negative volumes afterwards in the calculation, which is of course not what you want. So just do it as I do it here. So basically do it in if you think about it in the mathematical sense, so counterclockwise for the 2 planes, for the bottom plane and the top plane, and you have here, as you see, 1, 2, 3, 4, 5, 6, 7, 8. So if you number your elements like that, you will be fine. Yeah. Okay. What does this all about this object with finite elements? So basically you can build whole objects out of these. So this is called meshing. We'll go into meshing in details. We will build a very small mesh with just 2 elements in order to show off the functionality of all this and how everything works. But basically what you normally do is you build an object like this from small objects like this. What you want, of course, is that they don't change too much in size, so that basically the elements are in volume. Well, if they, of course, they're not all the same volume, but you don't want to have a squeezed element here on the surface or something like this. If it looks like that, of course, this would be perfect. This would be ideal somehow. And then what you want to do is basically you want to apply forces on this object and see, for instance, how this object deforms, what stresses these little elements are going through, and what this actually means. Yeah? And this way you can make your statical mechanical calculation. So you anchor some points, basically you put some forces on the others, and you see how the object deforms. And you can basically imagine that you can build bridges out of this and things like that, and airplanes and whatnot, and apply forces on wings or on the bridge as you imagine cars going over it, and see how the object reacts to these external forces. Yeah. This is all about finite elements. And the story here is, well, of course, the smaller your pieces are, the more you will calculate, and probably the more accurate your simulation will be if you don't get into numerical difficulties because your objects are too small or you run out of memory. Well, these are things that, of course, that you want to take into consideration, and of course it also takes, well, how much compute time you have available, yeah? But this is, for instance, very reasonable for a little object like this, and you can say, okay, I put some force in here and see how this deforms. We will even do a way simpler object than this one, but this is just as for illustration purposes here, yeah? So then the big trick around this finite element theory is that you do this because it's numerically easy solvable, yeah? What does it mean, numerically easily solvable? So as you see, you might have hexahedrons which are deformed like this in your object, and what we do, basically we find the parameterization. So we do a coordinate transformation, so we transform this from our x, y, z coordinate system for each element separately, just to note this, into a xi eta zeta coordinate system, where in this case, so for the element that we are using, for this hexahedral element, the element in this representation becomes a perfect cube using this transformation. So it's just a parameterization of these coordinates here, where you see that a cube where of course the edges are at here at -1, -1, -1, sorry, here back here, and here up here at +1, +1, +1. So basically these shapes are here going from somewhere from -1 to +1 in some axis, yeah, and spun like this, so that the axis goes through the middle of this cube, yeah. That's the basic idea, and this makes it very easily calculable then for the properties of this little object here, yeah. As you will see further during the calculation. So we just always keep in mind, for each element that you have in your object, you perform a coordinate transformation so that it looks like this. And how do you do this? You do this using shape functions. So here again you have the points, so where the points are. So 1 is at and whatever, and 2 is at here. And basically you transform all your little objects into coordinate systems like this, so that you can perform easily calculations on them. So how does this work? So you use what is called the shape functions. You can watch this through or go this through in your head. I won't get into all the details in detail. I mean, you have all the details on the slide, but as you see, basically you have your xi eta zeta representation, and using this sum, basically you can get a transformation, so a reparameterization from standard coordinates to this xi eta zeta coordinates, yeah, for these cube shapes. So you see that for each, so you have to do this for each coordinate 8 times, with the xi is basically the point. So this is xi will be here the x coordinate of this point here, so from 1 to 8. And you do the same thing for y and for z, and then you get basically a relation between x, y, and z, and xi eta zeta, yeah. So you get your coordinate transform, your space transformation using those shape functions, yeah. Looks quite complicated here, is less complicated. If you think about it, you can think this through in your head one day. That's the way it works, basically, yeah. And this works like any other coordinate transformation. So it's just as if you transform from, let's say, Euclidean coordinates to polar coordinates or something like this. Yeah. So just that you have here the shape functions, which basically take your hexahedron and transform it into a cube in this new with these coordinates in xi eta zeta space. Using this transformation. Okay, that's the way it is. So if you understood this, you basically already have half of understood of finite element theory. That's the way it is, or at least static finite element theory. Yeah. So we do this for these hexahedrons using those shape functions. If you would have used other elements, the idea is basically the same, but you would have different shape functions probably. Yeah, and that's the way it works out. Yeah. So then once you have this, well, what do you want to calculate? So as I said, one of the basic things that you do using finite elements is calculating this basically the deformations due to a force that is implied. So you have nodes here. If you look at the mesh like this, which are indexed with ij, so each point here is a node, and on each of these points you can apply force, and you want to basically see, well, how does the object deform under this force. Yeah? And of course you also have to define, well, which objects, which nodes degrees of freedom are fixed, so that the thing can't move. Yeah, because if everything can move, then the calculation doesn't work. Yeah, so you have to at least to fix the object somewhere. That's so much said about this. So we calculate this equation, which basically is a stiffness matrix. Here you have a displacement vector then, and here you have a force vector. Yeah, and of course these things then are in at the end you want to have this in x, y, z coordinates. Yeah, but that's the way it is. So we will show how using these tricks here we can calculate the stiffness matrix. So we do this element wise, and the basic idea is that you do this for each element and sum it basically at the right point. So for ij, where you have the coordinates here, into the global stiffness matrix from a more global mesh. Yeah. You can just linearly sum this, so you calculate one element by each other, so the stiffness matrix for one single element, you sum it at the right positions here, and this basically works. Yeah, of course, you know that ij are shared by elements, because there are several elements here that share basically, so this point here is at least shared by 3, this element, and this element, and this is a point ij in the stiffness matrix. Yeah. Don't worry about this. So all three, so you calculate the stiffness matrix for this one, for this one, for this one, sum it up at this point here if you want to in the matrix. So of course this also gives you indices for the other points, but you will get from all three elements parts of these points, and you just sum it up in the global matrix and it will be fine. Yeah, that's how it works out. Yeah. And here we have our displacement vector, as I said, and the external force that we apply. Yeah? And of course, I is the degree of freedom, and we have 3 degrees of freedom for each node. Yeah? That's the way it works. So the question is, well, how can you determine right now this K matrix in order to solve this equation? So that's one of the big deals. How can I get to have my stiffness matrix so that in the end I can solve this linear equation more or less. Yeah? So Kij, of course, is in general a sparse matrix because due to the way that this works. Yeah. So you have lots of zeros in this matrix. Just to keep that in time, and you can transform. So the way you index your mesh, you can do index transformations, which we won't go into detail to make it more diagonal. So several algorithms do this. The one implemented here doesn't do it, so you're up to your own to build your mesh correctly before you start this whole stuff. But you can do this basically. Yeah. And how you build this K here, basically using the strain displacement relation and Hooke's law, yeah, on each element. Yeah, that's the way it works out. So what does this look like? Yeah, so we have basically these two matrices which are important. So there is this B matrix, which is this strain displacement relation, and there is this D matrix, which is basically Hooke's law applied in 3D space. Yeah, so this can be derived, and you have to integrate over a volume. So the volume in this case is one single element. So as I said, we can do this element wise per element, and this here comes this trick into play with this volume integration why we do this coordinate transformation. Yeah, because then it gets very easily, so you can use these Gaussian quadrature points in order to perform this integration. We will talk about that later, but that basically this integration in order to do this very easily, we perform the coordinate transformation that we've shown, and this is basically why you do this finite element stuff. Yeah? So this K, in our case here, as we have hexahedral elements, it will become a 24 by 24 matrix for a single element. You can think about this 8 times 3 degrees of freedom, so 8 edge points, 3 degrees of freedom gets you a 24 by 24 matrix. Yeah. Okay. So right now let's go into these little matrices. So here it gets very interesting. So in order for this volume element here, for this TV, and also then of course for the expression of these matrices, we need what is called the Jacobian matrix. So that you know that if you transform from one space to the other, you have to change this TV by multiplying basically in here, so that the changement factor will be the determinant of this Jacobian matrix times the new volume element in the new space, which will be equal to the old volume element. So this is basically how coordinate transformations work. So I don't go into further details here. You have to review your math lessons for that. Yeah. So that's the way it is. So it's the Jacobi matrix. The determinant of the Jacobi matrix times du is basically dv. So here you have this Jacobi matrix. The way you have to write it down, so the way you have to calculate it from the shape functions that we have pointed out above. Yeah. And the story here is that then we have this strain displacement matrix, and we can see that this strain displacement matrix, this can be derived, that is basically from the shape functions into the derivative against the coordinates in x, y, z, or in Euclidean space, if you want to. And the story is, how do you get this? So if you look at these elements here, these elements, they come from the inverse of this Jacobian matrix. Yeah, so you can, just using the inverse of the Jacobian matrix, you can calculate the elements that you need here in this strain displacement matrix. So which basically gets you displacements of your element transformed into strain. So you can basically imagine where if you deform the element, you get some strain out of it, and this is the matrix which describes that. Yeah, that's the way it works. So you get these elements here, and you get them from this is basically a relation to these deformations here. Yeah. And so, as I've shown you, we need to, in order to calculate the stiffness matrix, we need to get this strain displacement relation together with Hooke's law and integrate about it, and that's basically it. So we have, so calculating this here is easy. You calculate the Jacobian matrix, you take the inverse of the Jacobian matrix, so you can really do the inverse, inverse 3 by 3 matrix, how you would calculate it maybe with for instance Gaussian elimination, and to build the inverse, and basically can then just read the components here and insert the components into this matrix here. Yeah. And then of course we have Hooke's law. So Hooke's law basically says, well, if you apply some force, and if then you release the force, the thing goes into another state, and basically Hooke's law tells you, well, if you push with a force, how much the object will deform. So normally linearly here, but here we have it in 3 dimensions. And of course, in order to understand Hooke's law, so it's a linear relation basically. So the idea is you apply some force, and linearly the object gets smaller. For instance, if I apply a force from one edge on the object, on a beam, for instance, let's imagine I put a force on the final edge of the beam, how much the beam gets smaller. And in order to do this, you need of course material constants. So you have normally this E modulus, which gives you this linear relation, but as this in 3D, and of course the object, when you push it at one side, it will bubble up at the other side. you also need the Poisson number, but you can find these material constants basically for known materials, and that's what you plug in there. So these are material constants that you look up somewhere. In the finite element solver that I'm presenting here, these material constants are fixed, so you don't have anisotropic materials. Basically, you could have anisotropic materials where the E modulus has different size in different directions. For instance, we don't have implemented this here in this system, so here you have only isotropic materials for the sake of simplicity. So if you push at one side, you get the same deformation as if you push at the other side. So in X, Y, Z. Because otherwise it would get complicated here, but that's the way it is. And then we have this, as I said, we have this basically this matrix here, which tells you basically what is the stress that is applicated from the strains that get out here. So these are these typical sigma values that you know, and this is very important because we can in the end for each element obtain the sigma values, and from the stress values basically we know well how much stress is the material going through, and will it break or won't it break. Just to tell you this, but whatsoever, so we need this matrix in order to first of all to calculate our deformations. So it's basically you plug in this, you transpose this first, you plug it in 4, then you put in this matrix here, and then you plug this on the other side here, and then you integrate, and then you get the 24 by 24 elements of the K matrix. That's all you have to do here. Okay, so you multiply this out and you get into that, and then it comes to the whole story why this is so intelligent to make this coordinate transform, because you can do this integration with the Gaussian quadrature points. So what does this mean? So if you have a volume with AXY in XYZ, as I've shown you, with this transformation that we have here, and you want to integrate this field here over this volume, you can do this with this coordinate transformation that I've shown you before, using those shape functions by calculating the J, which is very easy because as you look at these shape functions, they're very easily derivable, so you can derive them by hand and very easily plug this in and get your J matrix out there. So you get your J matrix and you get this A basically, and the story is, well, you can calculate this using 8 points, and this is almost perfect. So this is there isn't you can't even find really the rounding error if you do this using floating point math, and you just sum up over these 8 points here, plugging in these coordinates here as Ri, as we have made this coordinate transformation with the Jacobian. And using this sum here, you have basically calculated A over this little volume. That's the whole story. If that's how it works. So 8 points for the whole integration, a sum over 8 points using the Jacobian. That's why we do this this transformation to this cube going from -1 to 1. That's the whole story about it. And this way you basically can calculate your K relation, because I've just shown you that you plug in these 3 matrices, you do this integration, of course. So you plug in the sum over these 8 points, and you get your K matrix out of it. That's all that there is. Because of course this here is then described in dependent on xi eta zeta, as you well know. That's the way it is. Okay, so right now we have this here. We have our little K elements that I've talked you through, and once we have them, well, we have just to calculate basically this relation, and from this relation then we can derive all mechanical properties, because we know how the element has deformed, and we know basically what strain it has, and blah blah blah, and we know if the object might break or not, and that's the basic idea behind it. So what you need is, once you have this K basically built, as I've shown it before, using this stuff, then you're basically done. So if you want to know the basics about finite element, you got it here. That's all that there is to it. As I said, you can calculate this K element wise and sum it in there. Here we do this for each hexahedron using this stress strain and the strain displacement matrices. Basically, so the shape functions allow us to do this numerically. For those who want to get practical right away, go back to the practical stuff. Right now you got the basics about it. We continue a bit with the theory, just to get you all the theory that is implemented here in this finite element solver, because it's a bit more complicated. But maybe you're interested in that and you just continue to look at it. It's also very interesting because it shows you some basics, what people in this finite element field do, and why it's not as basic as it's here. Okay. So we have implemented in our elements what they're called these bubble functions. So these bubble functions are what is also called, so they're called either bubble functions or so-called non-conforming displacement nodes. Besides the degrees of freedom that we have from the shape functions, we basically add like 3 virtual shape functions, let's call it, to our element, and they allow them, as you see it here, is basically as a parable. So basically they allow them to wobble the element, and this allows to without going into all details, to overcome a problem which is called shear locking. So it eases the calculation of your or your finite elements in the end. It makes the system more numerically stable, if you want to. Let's express it like this. That's the way. So we added these three functions to the shape functions, but we don't, of course, change the shape in the end of the or at least the 8 points of our elements, but so they are not really connected to some, how should I say it, to some fixed point in XYZ space. But you will see how this all works. So using these virtual displacement nodes, of course, we extend our degrees of freedom. So we have to take these 3 bubble functions into account. And so basically the K matrix gets bigger here, of course, because you have more degrees of freedom. But of course you don't really have forces on the other side that act on them. So how do we cope with that? So we apply the matrix, and looks like this. And the trick here is you have this G matrix with these cross terms here. So you have the P matrix and the G matrix in here. As you see, basically with this G matrix here, we get basically this story up here. And the G matrix, well, how then do you calculate these elements? This looks very close to the P matrix, of course. How do we get these elements, this TP, so from our 3 functions here to these derivatives? And there's a special trick here, because it's not really calculated, but it's kind of, it's a trick. Let's say it like this. So you take your Jacobian, the Jacobian just as we have calculated it up there, you plug it in here, evaluating it, so the inverse of the Jacobian at 0. As I told you before, in order to do this for the standard B and not for the G here, so for the standard B you just take the Jacobian inverse and you get this here, and you don't do this trick, but here you take it at 0, and then you multiply it with this factor. So this here is the determinant here of the Jacobian, divided by the determinant of the current point that you're evaluating. Yeah, so in the other way, you just take the current point, you evaluate this with -1, and you get this here. But here we do this trick here in order to get these little derivatives. Look very well how this is calculated. So this is the Jacobian inverse evaluated at 0 times the Jacobian here evaluated at 0 divided by this Jacobian at the current point, and this basically kind of transforms you this TPI xi eta to this TPI derivative driven by x, y, z that we plug into this G matrix. Yeah, but the metric doesn't stop here. Yeah, so this all of this is just done in order to basically to have small correction factors to our calculation to perform the calculation easier. Yeah, let's say it like this. Yeah. And then people do something that is called static condensation. So static condensation basically is, of course, here you don't want to blow up your system, so you don't want, first of all, have a bigger matrix in order to perform the final calculation, because it's already hard to do this. I mean, hard to do. Yeah, you have numerical algorithms that we've implemented here in the algorithm in order, of course, to solve these linear systems rather quickly, but k gets very easily quite large, and then you add, let's say here, these coordinates, so you don't want to do this. And so what you really do is you reduce k, and you get these factors that are basically out there in these three matrices into this upper diagonal that you normally use for the standard calculation without doing these bubble functions. Yeah, and the way you do this is you kind of do Gauss elimination. So like as if you build the inverse here, which we don't put up here. Yeah, so that you basically build here a 1-by-1 matrix. Yeah, so you imagine you build the inverse and you do Gaussian elimination, and you put these factors up there into this little part without doing the whole Gaussian elimination, so just the partial one. So that you basically get all these factors up in there. Yeah, and this then I call this here G included, so this little matrix, yeah, where you kind of have moved all the factors up there, and this actually works. Yeah, this is kind of sounds crazy, looks crazy, but you basically perform a partial Gaussian elimination, and you get here basically a matrix which tells you that you can apply onto this in order to get this form here. Yeah, if you do this with this inverse method. But basically you can just trash this little matrix. You just push all these factors in there with your Gaussian elimination algorithm and get this little matrix. So we solve then for this, yeah, for this G included, so for this part after we have performed this Gaussian elimination. And that's how we do it. So that's all that is implemented in our algorithm. Of course, there are several tricks, implementation tricks in order to solve all these fast. The matrix here is sparse. You need a special algorithm in order to quickly find the elements of the matrix. You need a special algorithm basically in order to solve this system, as k can get very easily very, very big. Yeah, we did this. We are faster for this element than ANSYS, but of course ANSYS does a lot of things that we don't do. That's the way it is. Yeah, that's the way it works. So you don't have a graphical interface to this. You just have an input file, and I will show you how to do this practically and how all this looks like. Yeah, but this is a basic finite element solver that you can solve. Basically, you can build a virtual bridge out of these little hexahedrons, and imagine forces, put forces up there as if a truck goes over the bridge, and see how the bridge deforms. Things like that. You can do it with them. Yeah. Here I will just show you a very quick example. So how does this all work? How can you get running with this? How can you use this little finite element solver? So you have a more elaborate documentation than what I'm showing here in this little tutorial, let's call it like this. over here at GitHub, where you can download this. So this here you have a document basically where this is all described, how this works internally, and the little presentation that I've given you. And here you get the finite element solver, and we will head over here. So we will basically clone this in our system. Yeah, so we are here at the GitHub page. This here is basically the tool here. Please cite this with this Zenodo link if you use this, if you find this useful for your work. That's the way it is. Yeah. So this is very educational. Of course, all other finite element solver do maybe more elaborate things, but this is kind of a little tool in order to get started with finite elements. Yeah. So okay, so we can copy this here. And basically check out the repository here in our terminal. So we push up a terminal. You already know this from my other videos probably. So git clone, and we get here the finite element solver cloned into this directory. So this is always on a Unix machine. Of course, you can do this in Windows in services for Unix or something like this. This also compiles in Windows. This was tested, so all the functions have been made that you can basically compile this with a MingV or whatever compiler, or you probably even could compile this with Visual Studio in looking at the makefile and just compiling the individual objects and linking them together. Yeah. Okay, let's not go into details like this. Let's show off what this does. So you have this little directory here. You have some files in there, which basically which is basically the program here. We have a makefile as we're on a Unix system, and if you're on Ubuntu, for instance, you install your build essential. So apt-get install, you would perform apt-get install build essential, something like this. Essential, I'm not sure, build essential. So build essential, you will find it out. And then you get automake and all the stuff in order to compile this. You compile this with make, and this should be rather fast here. So as you see, this here is rather quickly compiled. There are several optimizations in there. It's not parallelized across different cores. It uses at several places, it uses basically AVX and SSE instructions in order to make it a bit faster. If you want to parallelize it, things like that, probably can be done. I didn't do it for this little experiment of my own, basically for this experience here to build this finite element solver. Yeah. It wasn't needed, yeah, so it was already faster than ANSYS with on one core with the way we did it. Yeah. Okay. How do you use this then? So you get out this hexfem binary here that we have here. So let's just make sure that this is the new one here. Yeah, we just compiled this here. And so basically you can use this, and there you get a sample input. And if I go to the sample input and I run this, what comes out of it? So as you saw, basically you get well, the displacements of the nodes. Yeah, so each node of course here has an index, and you get the displacements of the nodes. There you have 4 where you don't get any displacement, so these are the fixed nodes. Yeah. This is basically here. You see you have 12 nodes. I will show you in 3D what this looks like. These are just 2 elements stacked on top of each other in order to get you a very basic idea. So 2 elements stacked on top of each other. You have one surface which is shared by each other, so 4 nodes which are shared by each other. This makes you 12 nodes, 2 elements, and you get into that, and it looks the way it is. And of course you get the forces for the nodes that you have fixed. Yeah? So basically on the nodes that are restrained, you get forces out of them. What are the forces that act on them? Yeah, the others that are getting displaced, so you don't really get forces on them. Yeah, of course where you apply them. Yeah, but that's a different story. So we applied these forces here. We get these forces on the base of this object, and here basically on the top plane of these two stacked cuboid objects. Here we apply some forces and have this object deformed, and here you get for the individual nodes just the displacements of the individual nodes. And we also get here a post-processing out, so we get the strain tensor for each node, and we can calculate the principal strains. Of course, what we are interested in is the highest principal strain in such a calculation, which basically tells you, well, will the stuff break or not? That's kind of the story. And here you see you get volume before deformation, and this is the volume after we deformed it. So you see, of course, that the volumes of the elements change as you perform these deformation calculations here. Yeah, that's the whole story. So what does this look like practical? How can you get your own input file? So I will just go into the sample input that is shipped with it to walk you through what's the syntax here. So as I told you, this is ANSYS inspired, so that I could basically compare it also to ANSYS and take files from ANSYS and see if it makes the same, if it gets the same results. Yeah, this is not the complete same syntax as ANSYS. Look it up in the manual how it works. I will walk you through it here quickly. Yeah, it's very easy to understand. So you have the nodes. Yeah, each node has a number, and then you have an XYZ coordinate behind the node. Yeah, and this only, of course, does hexahedral elements. Yeah, not any complicated stuff, and it's very limited in what it does. But of course, it also does very cool stuff, because, as I said, you could calculate a bridge with it if you find the tool that builds you the mesh for it. And probably the idea is you use some kind of mesh out there, get you a script which transforms your nodes into this, yeah, and the elements into this, and get your mesh in there. But okay, so you have all the nodes up there. So basically, as I told you, these are two stacked cubes. So these here, the four ones here as this base. Cuboid objects, of course, hexahedrons, yeah, which are deformed, of course, is not cubes, but deformed objects. Sorry for that. So these two hexahedral elements that are stacked on top of each other and deformed to make it more fun, as you see. So this is not 1, 1, 1. Yeah. And we have this here, and then basically these here are the constraints. We only support this type of constraints. So where all the degrees of freedom are fixed for one node. Yeah, I know ANSYS basically supports that just maybe the x coordinate, the y or the z coordinate might be fixed here. In this little tool, we support only all coordinates fixed. That's the way it is. That's all that is implemented there. Yeah, but of course for the forces you can build in the forces as you like. So you can build your force vectors here. We just use the z direction. We could use the x, y, and directions too. Here you have basically which node is fixed. So 1, 2, 3, 4 is fixed, and we apply a force on 9, 10, 11, and 12. So on the top of this object. Yeah, and we see how it deforms under the pressure exercised by these forces up here. Yeah, that's the way it looks like. Yeah. Okay, then we have here the material constant. So this is, as I said, this is basically this Young modulus, and this is this Poisson number here that you basically put in there in order to describe, well, the strength of the material. Of course, if you have maybe iron, yeah, this is something different than if you use copper or things like that. And you have to look up the material constants that you want to use for your calculation. That's the way it works. Huh? And then, for the materials, basically this has to be above the element here, because it will be used for the elements that are successing here. Yeah. And how does the element look like? So how do I define an element? So as I said, we have all the nodes up here, and the element, basically it's just you type E and then you just type 8 points. So 8, so basically this is the first element, and these are the points that the second element is built of. And as you see, this here is the shared plane between the top and the bottom element. So this here is the top element if you think about it, and this here is the bottom element if you look at that here. Yeah, here's the z coordinate. Yeah, okay. That's the way it works. Yeah, and if you would have different materials, so you can have different materials, but the way it works in here is that it's by the as it's the way it reads it in the file. So you have if I would have a second type of material for the second node, I would have to put it in between this line and this line, and then it would take the material one for the first line and the second material for the second line. It doesn't work any different with this type of tool here. Yeah, okay. And then at the end you can type what you want to display. As here we displayed everything, so you have the displacements that you can display. As we've shown you, you can display the forces. So this ZU is just for output. This was my own creation here. And here basically you can say, okay, you want to see the strain. So this is kind of the strain matrix. You want to have the principal strains. So this calculates the eigenvalues of this strain tensor that we have here. And then you want to have the volume before and the volume after deformation for each element. This is basically what this tool can do. You can, in order to make your output smaller, you can leave out, if you don't need this, all the things, you can leave them out, and of course it eases also the calculation, because then it doesn't calculate it. The tool can only calculate everything at once, so you just count from one result and just calculate the other stuff. So either you put it in there before, or you don't have it, or you calculate it with a different tool. That's the way it works right now. Yeah, that's it's an educational tool where you have all this stuff in there, and that's the way it looks like. So we made our calculation, we got all these outputs here. As I showed you, we have here the coordinates. So we have here basically the initial coordinates here that I put in here. Yeah, I made this by hand here just as to have a quick example. I tested this, of course, with meshes which have thousands of nodes or thousands of elements even, and it works pretty fine. And in 3 to 4 minutes you have a even on one core on a very slow machine, you have a result. Yeah. So of course you can use this for way bigger things than this, but this here is a small example in order to show you basically that it works, and so that I can here just type enter as I show you here, and get this result that we have here with the displacements and the strains and the forces out here. Yeah, and so I took Blender and I took all these displacements here, and I took the original coordinates. So the original coordinates, then I add the displacements onto all the coordinates here, and in order to show you what is the result of this calculation, so that you can imagine it a bit better. So let's look into Blender. And we see here, so this here is X, Y, and Z, just as it is here in our input file. And let's put this window down here. And if you see here, so basically, as I told you, we have to go in these circles here. So this here is node 1, yeah. This here is node 2 here. This here is node 4. Node 5 is then back here, yeah. Node 4 is back here. This here is node 3. Node 4 is back here. Node 5 then is up here. Yeah, and then it continues like this. This here is node 6. This here is node 7, node 8. And then up here it's a bit convoluted because we have node 9 here, node 10 here, node 11 up there, and node 12 down there. Yeah, that's how it looks like. Yeah, two hexahedrons stacked on top of each other, and we apply forces here on the top, and we want to see how they deform. So this is already the input configuration. Yeah, so 2 deformed hexahedrons with these forces here on top. And if you look at it, so as I told you, well, 9 is here, 10 is here, 11 is here, and 12 is here. So you see that basically the forces on the edge over there are stronger than on the edge in the front. And we will see this because if right now I take so I inserted here 2 keyframes, and at the second keyframe, basically we're at the deformed state, and I can move here with this slider from the, let's say, from the initial state, so from the where no forces are applied, to the deformed state where the forces are applied, and you see how it tilts over there as the forces are bigger at the other edge than they are at the front edge. And this is then basically the, you see it here, the deformed object under the forces applied, how it reacts to these forces. Yeah, so it's fixed on the base, of course, because we can say this is like a standing sculpture, and there is this force applied with this Young modulus and Poisson number, and this is how it deforms. Okay, that's all there is to finite elements. Try out the code if you want to. Look at the code, play around with it, have fun, build your own stuff, build your own, so you have to do this all by hand with this tool here, but you can find tools that will probably, or write yourself scripts which transforms your hexahedral meshes into this type of story here. Use this input file, play around with it, play with the finite elements, have fun with it, calculate deformations as I've just shown you. This is what you get as an output. So for each node the deformation, for each node the volume, the strains, that's the way it is. I hope you had fun with this video, and this is all that I wanted to show you about finite elements, and I hope you had an introduction to finite elements, how it works, how you can play with it, how you do it. Of course, this year normally you would need way more elements in order to get the accurate calculation. This is just a small example to show you off how everything works. Okay, thanks for watching here, and I hope you had fun with this video.